Okay, we are on the third method for determining the deflection of a beam, which is method of superposition. So so the method of superposition is actually a popular method for finding the slope and deflections. So this is based on the principle of superposition. If the response of a structure is linear, then the effect of several loads acting simultaneously can be obtained by superposing or adding the effects of the individual load. So, which means that by linear response, we mean that the relationship between the cause referring to the loading and the effect, which is referring to the deformation and internal forces, is linear. So, the two requirements for linear response, the first, which is the material must obey the Hooke's law, and the second, the deformation must be sufficiently small so that the effects on the geometry is negligible. So we have to take note that the method of superposition permits us to use the known displacements and slope for simple load to obtain the deformation for more complicated loading. So which means that the method of superposition also allows us to identify or to determine, to solve for the displacements, talking about the deflection, and slope for a simple load to obtain the deformation for more complicated loadings. So using the method of superposition, we try to have and access to the table that is the list of the formulas for slope and deflection for various loading, such as we have your table 6.2 and 6.3. So these are the list of the formulas that we're going to use to solve for the slope and deflection for the various loading or for the different loading that is acting on the beam. So you have here you have here a series. This is actually table 6.2, which has the formulas for cantilever beams. So if you're going to observe, the beam is a cantilever. So only a fixed support on the other end, and the other end has no support. So basically, you have here different formulas to solve for the deflection as well as for the slope. So these are some of the formula for our deflection, and we have here formulas for the slope. So this one is this refers to our deflections. This one refers to our slope. So we have here different formulas that we will be using to solve for the deflection as well as for the slope of a cantilever beam. So which is dependent on the loading that is acting on the beam. So we have here concentrated load, uniform loading, as well as triangular loading, and we also have here a moment that is acting on the beam or a cantilever beam, and we have here specific formulas for deflections and for our slope. So we have here a continuation for our list of the formulas to solve for the deflection and slope for a simply supported beams. So we have here a simply supported beams with various loadings. The loadings are concentrated load, we have a uniform loading, and a triangular loading, as well as a moment that is acting on our beam. So we have here our different formulas to compute for the deflection as well as for the slope for the beam, dependent on the load or the load that is present on our simply supported beam. So the first problem is to compute the midspan value of EI small delta for the simply supported beam shown in our figure that is carrying a two concentrated load. So basically for this problem, we have to identify the formula that you will be using to solve for this given problem. So based on the table for the list of formulas that we have presented a while ago, there is a formula to compute for the deflection for a simply supported beam. So you refer to the second table that we have identified a while ago, that we have presented a while ago, which is deflections for simply supported beam. And since you are after for the formula, and we are after for the midspan value, so for a concentrated load with the midspan value, we refer to the figure in table 6.3. So based on table 6.3, we have for the deflection formula for simply supported beam. So you are going to make use of this equation. This is the equation that you're going to use. This is to compute for the deflection at the midspan for a simply supported beam. So for this one, we have to denote that our x here refers to our B. So, and we have, that is our B in our midspan, wherein our A is greater than B. So you have to take note that L refers to the length of the beam, and our A here is the distance from the support towards the concentrated load, as well as B is also the distance from the support to the concentrated load. And we have to take note that our A is always greater than B for this one. So using the equation from table 6.3, we have this EI is equal to this is EI, or this will be equivalent to, the formula actually is EI small delta at the center, that is the midspan value of EI delta, is equal to PB based on table 6.3 formula, all over 48 times 3L squared minus 4B squared. You have to take note that where A is greater than B. So based on that formula, we have to take note that we're going to get the deflection. Since in the tabulation, in the table, we don't have concentrated load for more than one concentrated load acting on the beam. The formula is for one concentrated load that is acting on the beam. So therefore, we have to get the deflection for each of the concentrated loads. So let's try with the deflection due to our 80 pounds concentrated load. So therefore, you have here our first computation. So we have here our 80 pounds. So you have to take note that you have to identify our A and B. So as mentioned, our A is greater than B. So this is our A from the support towards the concentrated load. So this is our B. So therefore, this is the elastic curve. We have here our midspan deflection. So that is sigmas deltas of 1. So therefore, if we're going to make use the formula, this formula, we can compute now for EI, sigmas deltas at the center, deltas of 1 at the center is equal to P, which is 80, times our B, which is 3. So our B here is 3. Then this is all over 48. Then times 3 times the length is actually, this is 3 times 12 squared minus 4 times 3 squared. So if we try to simplify this one, we get a value of 1,035 pounds cubic feet. So this is now due to the 80 concentrated load. So the second one is due to the 100 pounds. So we have here, so the support. So this is our 100 pounds. So therefore, this is our A, and this is our B. You have to take note that A is always greater than B. So therefore, uh, this will be our elastic curve. So this is deltas of 2. So we have here EI, deltas of 2 at the center, is equal to, substitute to this equation. So you have 100 times our B is 2 all over 48 times 3 times 12 squared minus 4 times 2 squared. If you try to simplify this one, you get a value of 946 pounds cubic feet. So therefore, if we try to get the midspan deflection of using the superposition, we simply have to add. We simply have to add the two deflections. So EI delta is equal to EI delta sub 1 plus EI delta sub 2. So if we try to add this, 1038 and plus 946, you have here a value of 1,981 pounds cubic feet. So this is our final answer. So the second problem is the simply supported beam in the figure carries a uniformly distributed load over part of its length. Compute the midspan displacement. So we're going to compute for EI small delta. So the formula that you will be using is based on this figure table 6.3. So the uniform load, the load that is present on our beam is uniform loaded, but it is it's the uniform loading is not for the whole it's not present on the whole span of the beam. So this is the illustration for our figure in our problem. So this is the formula for this. At the center for the deflection, midspan deflection, is this one. So this is the formula that you will be using to compute for the midspan deflection. So you have here our equation. So we have to take note, based on our figure, our uniform loading is from a certain point on the beam towards the support. So in our illustration, our uniform loading does not extend to a certain support. So we have to extend our uniform loading towards the support. So this is our figure. So as mentioned, it doesn't the uniform load does not extend to our support. So the formula that you will be using actually is EI at the midspan is equal to W sub O all over 384 times 5 L to the fourth minus 12 L squared B squared plus 8B squared. This is the formula from table 6.3 for a uniform loading. So basically for this, if you're going to compute for the deflection, you have this equation for our beam. However, in this formula is applicable if this uniform loading extend up to the support. So therefore, we have to extend our uniform loading to the support. So which means that we will have here our illustration. So this would be the illustration for our beam, so that we can make use of the equation. So therefore, this is our B and this is our A. So if we're going to make use of that formula, so this is our sigmas of 1. So we can, if whatever we have added